Online Analyzer Tutorial Part 1. General Purpose of Analyzer Houses. Analyzer houses are essential for ensuring the continuous, reliable operation of online analyzer systems by offering a controlled and protected environment. These buildings shield sensitive instrumentation from environmental hazards such as extreme temperatures, high humidity, dust, and corrosive sulfurous air. The quality and stability of the analyzer environment directly affect the performance, calibration stability, and lifespan of the instruments housed within. Their construction should only be considered where operational needs cannot be satisfied by simpler solutions, such as walk-in shelters. Due to their complexity and cost, analyzer houses contribute significantly to total cost of ownership. Accordingly, their deployment must be justified by operational necessity, safety requirements, or environmental constraints. Evaluation of alternatives should focus on lifecycle performance, space utilization, and overall cost effectiveness. Basis of design. The core objective of the analyzer house design is to ensure that the internal environment remains non-hazardous, regardless of external conditions. This is achieved through continuous artificial ventilation, appropriate zoning, and the use of protective measures that detect and respond to deviations from safe conditions. The design must also support electrical safety systems, temperature and humidity regulation, and mechanisms for safe shutdown in the event of ventilation failure. Designers must include verification and testing of protective systems, define allowable climatic conditioning limits, and establish contingency measures for equipment shutdown during failure scenarios. Where toxic or hazardous materials from the process environment are involved, additional safeguards must be identified through hazard studies and explicitly incorporated into the design. Forced ventilation is the default assumption for all analyzer houses. Induced or natural ventilation methods are not acceptable substitutes. Safety studies must address risks arising from both internal sample handling and external environmental exposures. Protective measures must be tailored to the hazard profiles identified during these analyses. Basic design standards. The design of analyzer houses must comply with established international standards. Key references include IEC TR 60079-16, which outlines procedures for using artificial ventilation to achieve a safe area classification inside analyzer houses. IEC 61285, which provides guidance on the general safety, layout, and integrity of analyzer installations. IP 15, Institute of Petroleum Model Code of Safe Practice, Part 15, which specifies ventilation requirements and area classification methodology. These standards collectively ensure that analyzer houses are constructed and operated in a manner that maintains safety, supports operational reliability, and aligns with recognized best practices in hazardous area design. Health, Safety, and Environmental, HSE, considerations. The safe operation of analyzer houses relies on robust health, safety, and environmental measures. The amount of flammable material entering the house must be minimized, and ventilation systems must continuously dilute any accidental gas release to keep concentrations below flammable limits, as recommended by IEC TR 679-16 Hein. In the event of ventilation failure, additional precautions must isolate electrical circuits and trigger alarms. Environmental management includes safe disposal of vent gases and liquid effluents. Hydrocarbon-contaminated waste must be directed to recovery systems or compliant disposal infrastructure. Water potentially contaminated by chemicals must be isolated from general drainage to avoid impacting biological wastewater treatment systems. Fire protection systems must also be included in the design with features such as alarm panels, emergency lighting, evacuation indicators, and gas detection systems. These systems must be verified before commissioning and periodically tested during operation to ensure readiness under emergency conditions. Through strict adherence to international codes, rigorous HSE design integration, and careful assessment of operational risks, analyzer houses can deliver high-performance analytical capability while protecting personnel, the environment, and equipment. Online Analyzer Tutorial Part 2. Applicability of online analyzers. Online analyzers are instrumental in providing continuous, real-time measurements of critical process variables, enabling enhanced process control optimization, safety, and compliance monitoring. Their use spans a wide range of industrial sectors, including oil and gas, petrochemicals, refining, power generation, pharmaceuticals, and water treatment. Online analysis improves process transparency, reduces product variability, minimizes emissions, and increases plant efficiency by allowing timely process adjustments. The selection of online analyzers depends on process characteristics, required accuracy, response time, sample composition, maintenance strategy, and integration with the plant's automation systems. Common applications include monitoring of gas composition, e.g., O2, CO, CO2, H2S, hydrocarbons, liquid phase properties, e.g., pH, conductivity, density TOC, and process quality indicators, e.g., octane number, moisture content, flash point. Critical use cases. Online analyzers are especially valuable in situations where manual sampling is unsafe, impractical, or too slow for process needs. Product quality must be tightly controlled within narrow limits. Emission levels must be continuously recorded to meet regulatory obligations. Process safety depends on maintaining certain gas compositions or concentrations. Real-time feedback is required to enable automated closed-loop control. Typical installations include process streams and flare gas monitoring, continuous emissions monitoring systems (CEMS), fuel gas conditioning, reactor effluent analysis, utility systems, e.g., boiler feed water, custody transfer metering, and environmental monitoring stations. Limitations and constraints. While online analyzers provide significant advantages, there are also limitations that must be considered during scope definition. These include high capital and operating costs relative to field instruments, regular calibration and maintenance needs, especially for optical and wet chemistry systems, sensitivity to contaminants or sample conditioning failures, response time delays due to long sample transport lines or lag in sample conditioning systems, requirement for sample representativeness and flow consistency. Additionally, online analyzers are best suited for stable process conditions where the sampling rate and signal processing intervals can align with the dynamics of the control loop or monitoring application. In highly transient conditions, fast response field sensors may offer better control loop performance. Integration and interfacing. Online analyzers must be seamlessly integrated into the plant's process control and automation architecture. They typically interface via 420 milliamps analog signals, Modbus RTU TCP, Profibus, HART, or OPC UA, depending on the type of analyzer and host system. Integration points must include not just measurement outputs, but also status flags, alarm bits, maintenance indicators, and diagnostic information. In many installations, analyzers are part of a distributed control system, DCS, safety instrumented system, SIS, or supervisory data acquisition system, SCADA. The analyzer data may be used for direct control actions, trend analysis, regulatory reporting, or predictive maintenance, requiring reliability, traceability, and cybersecurity compliance. Suitability assessment and specification. Prior to selection, a suitability assessment must be performed. This includes evaluating process conditions, pressure, temperature, composition, required accuracy, range, and resolution, sample conditioning requirements, cooling, filtration, phase separation, installation environment, explosive atmosphere, marine air, high vibration, maintenance, accessibility, and analyzer house infrastructure. Specification of an analyzer system must also cover performance guarantees, calibration protocols, warm-up time, drift behavior, sample return disposal methods, and operating envelope. Vendors should provide validation data, integration protocols, and documented field experience. Role in operational excellence. Online analyzers directly contribute to key performance indicators, KPIs, such as yield improvement, energy efficiency, waste reduction, and safety compliance. By reducing dependency on manual sampling and laboratory testing, they improve process visibility and decision-making accuracy. Their use in model predictive control, MPC, advanced process control, APC, and alarm management systems further amplifies their impact on plant productivity and stability. Compliance and regulatory drivers. Certain applications of online analyzers are legally mandated, particularly in environmental monitoring. For example, continuous emission monitoring systems, CEMS, are required under air quality regulations. Flare gas monitoring is mandated to limit emissions of unburnt hydrocarbons. Water discharge monitoring, TOC, COD, conductivity, is enforced to prevent environmental contamination. These compliance drivers impose specific requirements for analyzer performance, uptime, data retention, and validation protocols, making it critical that the analyzer scope is matched with current and anticipated regulatory standards. Operational lifecycle support. Defining the scope also involves long-term support planning. Service contracts, spare parts strategies, calibration schedules, and field technician training must be included in the overall project lifecycle. A poorly supported analyzer, even if well specified, can quickly degrade into a liability. Therefore, vendor support structure, installed base, and regional servicing capabilities should factor into scope decisions. Conclusion. The scope of application for online analyzers extends beyond measurement. It touches product quality, regulatory compliance, operational efficiency, and plant safety. Defining this scope with clarity ensures that analyzer systems are technically appropriate, economically viable, and operationally sustainable. With proper integration, support, and risk analysis, online analyzers become critical assets in the pursuit of high-performance process automation. Online Analyzer Tutorial, Part 3. The design philosophy for online analyzer systems must focus on ensuring reliable performance, ease of maintenance, personnel safety, and compliance with recognized international standards. Analyzer installations are more than individual devices. They are systems comprising sample takeoff, sample transport, sample conditioning, measurement, calibration, data communication, venting, and enclosure. These subsystems must be harmonized and engineered as an integrated unit. Successful analyzer design begins with a clear understanding of process requirements and the physical and chemical properties of the sample. Key design drivers include response time, sample representativeness, environmental conditions, maintenance accessibility, and safety. As analyzer installations often operate in harsh or hazardous environments, designs must ensure robust operation, minimal drift, and support for fault detection and recovery. Environmental and area classification considerations. Online analyzers are frequently installed in hazardous areas, Zone 1 or Zone 2, and exposed to aggressive industrial environments, including high salinity, dust, vibration, and temperature extremes. The design must comply with area classification standards, e.g. IEC 6079-10-1 for gas atmospheres, and all equipment must be certified accordingly, e.g. XD EXIA XN. Overpressure protection or gas-purged analyzer houses may be required to allow safe operation of general-purpose equipment in classified zones. In addition to explosive atmospheres, designers must address non-classified environmental hazards such as high ambient temperatures, humidity, UV radiation, and corrosive substances. Enclosure ratings, e.g. IP65 or better, and material selection, e.g. stainless steel for coastal installations, are critical for long-term performance. Sample handling and conditioning philosophy. Reliable operation of online analyzers is dependent on proper sample handling. Sample takeoff points must be representative of the process stream and located to minimize dead volume, delay time, or contamination. Sample lines should be as short as possible, with appropriate slope, heat tracing, and insulation to avoid condensation, plugging, or phase separation. Sample conditioning systems, such as filters, regulators, chillers, or vaporizing probes, must be tailored to the specific analyzer type and process fluid. Design should maintain the physical and chemical integrity of the sample, matching the analyzer's operating pressure, temperature, and flow requirements. Continuous flow must be ensured to avoid analyzer starvation and support consistent response times. Safety and isolation philosophy. Designs must provide the capability to isolate and depressurize analyzer systems during maintenance or in emergencies. This includes block and bleed valves, purge provisions, and flow restricting or excess flow devices. For analyzers connected to flammable or toxic streams, fail-safe isolation and automatic purging are mandatory to ensure personnel safety during intervention. In toxic service, or when working with pressurized flammable gases, gas detectors and interlocks must be included. Proper venting systems, with discharge routed to safe locations, must be implemented. All vent lines must be pressure rated and protected against water ingress or blockage. Accessibility and maintainability. Ease of maintenance must be embedded into the design from the outset. All analyzers and sample conditioning components should be accessible from walkways or platforms without requiring scaffold erection or confined space entry. Enclosures should be swing out or slide out for servicing, and components should be modular and clearly labeled. Proper layout within analyzer houses or shelters must allow for technician movement, ventilation, lighting, and placement of service tools. Sampling panels should include test points, calibration, gas ports, and pressure indicators to support troubleshooting and performance verification without interrupting the process. Redundancy and availability. For critical applications, redundancy in analyzers, sample lines, and control logic should be considered. Dual analyzers can provide automatic switchover in the event of failure or allow one unit to undergo calibration while the other remains online. Sample probes and valves should be designed to permit removal without shutting down the process. Designs must also address analyzer warm-up time, restart behavior, and data validity on startup. Inclusion of bypass lines, fast loop sampling systems, and buffered signal output can help maintain continuity of operation even during brief interruptions. Compliance with international standards. All analyzer systems and associated equipment must comply with relevant international codes and standards, including IEC 6079 series for electrical equipment, in explosive atmospheres 61110-1 for safety requirements of electrical measurement equipment, IEC 61285 for safety of analyzer installations, IEC 6079 for artificial ventilation of analyzer enclosures, API 555 for process analyzer systems design guidelines, for area classification and ventilation practices in hydrocarbon facilities. These standards govern not only the selection of analyzer components, but also the engineering of sample systems, integration with control systems, safety protocols, and ventilation arrangements. Instrumentation and electrical interface. Analyzers must be equipped with signal interfaces that match the plant's automation infrastructure. These may include 4 to 20 milliamps analog outputs, HART communication, Modbus, Profibus, or Ethernet protocols. Power supplies must be stabilized and backed up, and instrument wiring must follow segregation, shielding, and EMC compliance rules. Control system integration must include alarm mapping, instrument diagnostics, and state management, e.g., maintenance mode, calibration in progress, fault condition. Analyzer signals should be designed with clear status flags to distinguish between valid data, hold modes, and fault conditions. Documentation and handover requirements. At the completion of design, a full documentation package must be prepared, including general arrangement drawings, sample handling schematics, electrical loop diagrams, calibration procedures, safety function descriptions, startup and shutdown sequences, manufacturer data and certification. These documents support commissioning, operator training, and long-term system maintenance. Conclusion. A well-executed design philosophy for online analyzer systems ensures that the installation will be safe, maintainable, and reliable over its life cycle. By integrating safety, compliance, sample integrity, and maintainability into every element, from probe to signal output, the system becomes a resilient and valuable asset in process monitoring and optimization.